Yeah, if you like, okay, so you can turn the annotation, okay, so draw the molecule, okay, so to its mass spectrum, okay. Oh yeah, if you like, you can also write your answer in the chat window, okay. Right, so take a try, okay. All right, so when are you working on this question, okay, just see the one reminder, okay, so we have quiz 6 here tonight from 8 to 11. And make sure you bring your IR table and those NMR table. NMR table include proton NMR and those carbon NMR. Okay, so we need those finish the quiz here tonight. Okay, and I also have actual office hour. Okay, so from the 2 to 6. Okay, just after just right after this lecture. Okay, so if you have any questions, okay, please just the log back to the Zoom. Okay. All right, take a try, okay? Right, so we learned in the previous lecture, okay? So some the atom can give very special isotopic pattern, okay? So and those are the nitrogen rule, okay? So that you can apply it to this full spectrum, okay? Identify which one match the which molecule, okay? All right, take a try. Anyone know the answer? Okay, so you can also draw the answer in the window, okay, on the screen. Right. Okay. Remember the nitrogen rule we learned kind of if the molecular ion mass is odd number, okay, there will be odd number of nitrogen, okay. So which of these has nitrogen? Yeah, that's right. Okay. All right. So that's the nitrogen rule, okay. So odd mass, that will be kind of odd number of nitrogen, okay. So in this case here, the only odd number is here the 93 here, okay. So this one should match the aniline, okay. All right, okay, can anyone tell me what atom contain this this mass spectrum? All right, what's atom, okay? Which one match with the last one? All right. Yeah, bromine, okay, that's right, okay. So remember, okay, so isotopic pattern, okay, so for bromine, M plus 2, okay, so that should be 1-to-1, intensity, okay. I'm the 2M plus 2 ratio, about 1-to-1 ratio, okay, so bromine, okay. Right, can anyone tell me what's the atom in this molecule, okay, in this mass spectrum? Right, look at the intensity M2, M plus 2, okay. That's right, chlorine, okay, so chlorine isotopic pattern M2, M plus 2, okay, so 3-to-1, okay, so that's your typical kind of the chlorine isotopic pattern, okay. So those please keep in mind, okay. So in this case the last one, okay, 94 should be kind of this phenol, okay. 1-to-1 bromine, 1-to-3, okay, M2, M plus 2, okay. So 1-to-3, so chlorine, and then this one odd number, that's nitrogen, okay. Last one, okay. So those kind of important, okay, help you figure out any kind of heat atom, especially chlorine, bromine, or nitrogen in the molecule, okay. So that's mass spectrum characteristic. All right, okay, we continue chapter 15, okay. So although here the knowledge won't test in the quiz tonight, okay, but I want you a little bit focus on, okay. So today we cover some kind of most important information kind of about the mass spectrum, okay. So the first one is the fragmentation, okay. So we learned that so for the EIMS, okay, so yeah, the molecular ion, okay, so not so stable, quickly kind of break into the small pieces, okay, fragmentation, okay. So there are two types of fragmentation, okay. So one is the molecular ion break up, okay, yield one kind of neutral radical, okay, so and a carbocation, okay. All right, so that's the first one, okay. So this is the molecular radical, okay, molecular ion, okay, and then one's kind of the fragment, okay. It will generate kind of carbon cation. So carbon cation is the positive charge species, okay, plus the radical, okay. So this is the neutral radical, okay. Right. So keep in mind, okay. So mass spectrum can only detect charge species, okay. So that means can only detect the carbon cation, okay. Neutral radical cannot be detected, okay. All right. So here comes question, okay. So if the fragmentation can be anywhere or kind of a very specific kind of the position, okay. So answer is kind of there's some special rule, okay. So to break up the certain the molecule, okay, into a fragment, okay. So that's come to kind of the stability of the carbon cation, okay. Here's kind of one example, molecular radical, okay. So cation radical break up kind of the carbocation plus one neutral radical, okay. Right, and then it depends on the stability of the carbocation, okay. Right, so that's right down here, okay. So more stable carbocation, okay, the stability of carbocation, okay, is the benzoic carbocation, okay. So that's like this, okay. So CH2 are kind of the cation here, okay. This one we call it benzoic cation. And followed by allylic cation, okay. Allylic cation from the alkene, okay. So this one, okay. And then followed by the tertiary cation, okay. Tertiary cation, okay, just kind of the one center carbon, surrounded by three alkyl group, okay. That's the tertiary cation, okay. And then followed by a secondary cation, okay. Secondary cation, okay. So two alkyl group, okay, and then one hydrogen, okay, and then center carbon kind of cation, okay. And then followed by primary carbon cation, okay. So that's just two hydrogen now, okay. Okay, and the least stable one is the methyl cation, okay. Right, so that's follow this order, okay. So when the fragmentation happens, okay, so you try to generate kind of the most stable carbon cation, okay. And actually for the radical, okay, also pretty much follow the same order, okay. So more stable radical is the benzoic radical. Radical is kind of just the single the electrons here, okay. And then followed by the allylic radical, followed by the tertiary radical, okay. And then followed by secondary radical. And then followed by kind of the primary radical, okay. And the least stable is the methyl radical, okay. Right, and in the same order, but just the difference, okay, different stability kind of not as significant as the carbon cation, okay. So in other words, kind of the energy gap, okay. So the difference in their energy, okay. So carbon cation kind of bigger, okay, compared with the radical kind of the ranking, okay. Right. So in this case, the same kind of as radical, but not as unstable, okay, and so similar difference, okay, smaller. Okay, so that's the first type of the fragmentation, okay, and then second type of fragmentation is the molecular kind of the radical cation, okay, generates here the radical cation plus one neutral molecule, okay. To the fragmentation, okay. So this time this radical has the positive charge, okay. and then same time, yeah, you release a neutral molecule, okay. So this one has a positive charge, okay, and then actually for mass the spectrometer, okay, can detect this radical cation, okay, because the mass spectrometer can detect only charged species, okay, but cannot detect this neutral molecule, okay. And for this second type of the fragmentation kind of last the common. And normally, if you the molecule kind of release water or kind of carbon dioxide, okay, you can see this kind of the fragmentation. Okay, so one example is alcohol. Okay, so alcohol quite often eliminate water. Okay, so release kind of the neutral molecule, that's water, and also the radical cation. Okay. And for this process, okay, so more complicated compared with the first type of fragmentation, okay, because it involves multiple electron transfer, okay. So normally speaking, we use this this arrow, okay, we call it a full arrow, okay, indicate the transfer of 2 electrons, okay, and then use this we call the single barred arrow, okay, indicate kind of transfer of single electrons, okay. This one full 2 electrons, this one 1 electron, okay. And so far, you don't need to understand the how to kind of transfer electron, how this whole process. Okay. The little bit keep in mind. Okay, so this full arrow shows 2 electron transfer, and this this we call kind of we should also call kind of fish hook arrow. Okay, so that's here shows 1 electron transfer. We'll learn more in the radical reaction. Okay. All right. Okay. So now we can study kind of all the different kind of functional group there fragmentation, okay. First one is linear alkene, okay. So for linear alkene, okay, just break up here the individual bond, okay. So normally you can break up here from end of the carbon chain, okay, one by one, okay. And so but here the more common case, so you break up kind of middle kind of in carbon chain, okay. The reason for that kind of if you break up from the end of the carbon chain, okay, so you release either radical methyl group, okay, or kind of the methyl carbon cation, okay. So both kind of very unstable, okay. So last kind of the likely, okay. And but if you break the bond in the middle of the carbon chain, okay, so you can generate the relatively stable the primary the carbon cation and also primary the radical, okay. So primary is more stable than the methyl the carbon cation and also the radical, okay. And so for the linear alkene, okay, quite often you see kind of we call the ladder pattern of the fragmentation, okay. So quite often you see kind of IMP, okay, and I'm minus 15, and then I'm minus 29, okay, and then I'm minus 43, and then go ahead, okay, until 43, 29, 15, okay. Right. So if you look at the mass difference between all these fragments, okay, there's very special rules, okay. So let's maybe draw like this, okay. Right. So this is IMP, okay, and then next fragmentation, okay. So you find kind of difference, okay. So it's 15, okay, and then from the first fragment to the second fragment, okay, the difference is about kind of 14, and then 14 again, and then 14 again, okay. Okay, this process. Okay. The reason for that kind of the first time you break up C3, okay, so CH3. And then second time, okay, so continue break up kind of CH2, 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 okay. So that's the whole process, okay. So the CH2 mass is 14, okay. So that's why for the carbon chain the linear alkene, okay, you see kind of the series the 14 units can difference, okay, between the fragment and the mass, okay. That's very unique, okay, for the linear alkene, okay. Right, and then for the branch alkene, okay, so the preferred the breakup point is just on either side of the branch, okay. The reason for that is yeah, you can generate a more stable secondary carbon cation. Okay, so yeah, break it up here. Okay, here more stable subcation and also here. Okay, so yeah, normally the more branched fragment take the charge. Okay, so yeah, if you break up here, okay, so you generate kind of a primary, kind of yeah. Radical and then secondary kind of carbon cation. Okay, so yeah, normally you want the charge on the more branched species. Okay, so yeah, that's second carbon cation more stable than primary carbon cation. Okay, and so that's the keep in mind. Okay, so yeah, we can't kind of the branch. Okay, so and then yeah, the charge on the branch, yeah, more branch species. Okay, right, maybe right a little bit down. Okay, so branch arcing. Okay, so yeah, so you generated the break either side of the branch. Okay. Right, so all right, okay, next case, so we move to the alkene. Okay, yeah, so here's one example. Okay, so yeah, branch alkene. So yeah, two methyl pentene. Okay, so yeah, you can see the two highest peak. Okay, actually kind of corresponding to the break up either side of branch, and then the more branch the fragment. Okay, take the charge. Okay, so yeah, 71 and 43. Okay. All right, so next the alkene. Okay. So if alkene is a terminal alkene is kind of C double at the end of the carbon chain. Okay? So quite often you should see kind of allylic here the carbon cation. Okay? Allylic carbon cation. Okay? So yeah, we just learned it. It's very stable. Okay? So yeah, the one of the most stable the carbon cation. Okay? Let's see like this. Okay. Right, and then the mass of allylic carbon cation is 41. Okay. Because there's okay, that's just learn it. Okay, so yeah, here allylic carbon cation. Okay, so yeah, very stable. Okay, and because the stability of this species. Okay, so then yeah, you can see quite often the base peak. Okay, base ion. Okay, so yeah, that's the most abundant the fragment. Okay, so yeah, it's here from the allylic cation. Okay, so yeah, the highest peak. Okay, so that's here very unique for the carbon cation. Okay, for the alkene. Okay. And the similar thing for the benzene compound. Okay, so yeah, if there's RQ group, okay, RQ group attached to the benzene, okay, so quite often you should see benzoic here the cation. Write it down. If it's kind of benzene compound, you should see a benzoic cation. Okay, also called kind of benzoic carbon cation. Okay, and this one is probably more stable the cation we learned so far. Okay. And so the mass of your benzoic cation is 91. Okay, so yeah, because of high stability of this species. Okay, and so yeah, the base peak normally is just showed kind of the 91. Okay, and the highest peak also very unique for benzene. Okay, so if you see kind of a 91 peak, okay, so 99% are the benzene in the molecule. Okay. So next is alcohol. Okay, so alcohol, yeah, similar to branch alkene. Okay, so yeah, prefer break up either side of the OH attached alkene. Okay, so the branch side. Okay, so the reason for that is the resonance stability. Okay, so yeah, because for oxygen has lone pair electrons, okay, can shift the electron down. Okay, so in this case the positive charge can delocalize into this carbon and oxygen. Okay, so if you can delocalize the positive charge. Okay, so that's you can make this cation more stable. Okay, right, and that's also showed here. Okay. But quite often, okay, so yeah, they see the fragment, okay, hard to say, okay, because you don't know what's kind of the branch happened. Okay. And last year, the unique for the alcohol. Okay, more unique fragmentation for the alcohol is the I-18. Okay, so that's actually kind of pretty unique for the alcohol. Okay, so you should see one peak. Okay, so that's here the 18 less than mass ionic the molecular mass. Okay, So this one actually 18, we know that is here the lose one water, okay? So that's here the only happen to alcohol, very unique, okay? And the example showed here, okay, so yeah, this is here the butyl alcohol, okay, so that's here the IMPK, and then you can see kind of here the highest peak is here the I minus 18 and minus water, okay, so that's here very unique, okay, so yeah, for the alcohol, okay. And also here because the whole process, okay, so yeah, you lose one water, okay, so yeah, this fragment, okay, you should see kind of here the even number, okay. So far, yeah, most of the fragmentation case, so yeah, the fragment case, so yeah, the mass is kind of odd number, okay, odd number you see here, okay, odd number, okay, but here kind of the even number, okay, so that's pretty unique, okay. And then next kind of aldehyde ketone, okay. So aldehyde ketone, yeah, similar to yeah, alcohol, also yeah, branched yeah, the alkene, okay. So yeah, prefer break up here the just here the on the just next to here the carbonyl group, okay, either side, okay, branched position, okay. Also similar reason, okay, so yeah, because oxygen you can delocalize here the positive charge, okay, so yeah, then yeah, do the rest, okay, and generate kind of yeah, more stable fragment, okay. And so yeah, if there's the acetal group in the aldehyde ketone, okay, acetal we know that is the CH3, okay, okay, so that's acetal group, okay. In the aldehyde ketone case, so yeah, quite often you will see we call the acylium the carbocation, okay, so acylium carbocation, okay, like this. So the mass of acylium the carbocation is the 43, okay. So that yeah, if you there's the acetal group, okay, in the aldehyde ketone, you should see there for this piece the species, okay. So yeah. And the only thing, the problem kind of someone maybe already noticed, okay, so the mass of the acylium cation is kind of same as the 43k from the linear alkene, okay, so that's sometimes get confused, okay, so that's won't be so unique, okay. And but the one fragmentation, the very unique for aldehyde ketones, we call it the lefty kind of rearrangement case. So this one you will generate the even number of the fragment case. Oh, right down here. Yeah, lefty the rearrangement case. So this is the second type of the fragmentation case. So you generate the neutral molecule and those the neutral neutral the molecule and the radical cation, okay. So yeah, the whole process, okay, so it looks like you try to kind of the restructure and then shift the electron multiple times, okay. So this the process, you don't need to understand, okay. So keep in mind, okay, once it's done, okay, you generate the neutral molecule and those the radical cation. This radical cation mass is kind of the even number, okay. Okay, so yeah, show here, okay. Okay, so if you have an acetal group in the molecule aldehyde ketone, this the lefty kind of rearrangement, you should see kind of 58 kind of the fragment, okay. So yeah, even number, okay, again, okay. So if you combine these two fragments, okay, so the acylium kind of fragment and also the lefty kind of rearrangement fragment, okay, so that's here can determine it should be aldehyde ketone, okay. So very unique, but sometimes kind of not easy to observe it, okay. Right. And in the end, is the capsic acid, okay. So capsic acid kind of the fragmentation, also quite unique, okay. So yeah, you should see kind of the M minus 17, the fragment, okay. So M is the still molecular ion mass, okay. And then minus 17 actually kind of indicate kind of released one kind of OH group, okay. So yeah, from capsic acid group, it's kind of here, okay. So cleave of OH group, okay. So that's why you get kind of M minus 17. And another common fragmentation in the capacity kind of M minus 45. Okay, so that's actually clear off a whole of the capacity group. Okay, COH. Okay, example showed here. Okay, so this is the ion peak. Okay, so the molecular ion peak. Okay, so 152. Okay, and then you see kind of difference between the M52 and then this the fragment. Okay, 135 with the 17. Okay, so that's actually kind of the capacity. Okay, you released one OH group. Okay, and then another the fragment is the 107. Okay, so if you check it different to some mass. Okay. 107, 152 minus 107, you get kind of 45. Okay, so that's clear off the whole we call it kind of capacity group. Okay, right. Okay, and then for you guys, okay, so just a little bit keeping idea. Okay, so what's the fragmentation? Okay, so but most important kind of these three guys. Okay, so that you have to memorize the case. So because these three fragment. Okay, so quite kind of a unique mass and also high intensity. Okay, so first, okay, so if you see the 41 fragment, okay, mass is 41. Okay, 99% are the alkene group in the molecule. Okay, second kind of if you see 91 fragment, okay, so that means there's benzene in the molecule. Okay, and last one is kind of if you see the one fragment is the 18 less than kind of your molecular mass. Okay, so that means it's alcohol. Okay, so this mass also be kind of the even number. Okay, so those three please memorize. Okay, other okay, so just a little bit keeping idea. Okay, so sometimes kind of you can see this kind of fragment. Sometimes you cannot see it. Okay, so sometimes kind of maybe some kind of overlap. Okay, so confusing. Okay, like this 243 peaks. Okay, so maybe from kind of ketone, maybe from kind of linear alkene. Okay. But these three, okay, please remember it. Okay. All right, okay, so now we can do a little bit of practice. Okay. All right, so we have this mass spectrum. Okay, showed here. Okay, can anyone tell me what kind of functional group in this molecule? All right, take a look. Okay. So the ion peak already labeled it. So that's the molecular ion mass is the 100, and then we have two fragments, okay, 82, and also the 57. Okay, can anyone tell me what's the functional group in this molecule? Okay. All right. So anyone want to take a try? Okay. Yeah, just based on the knowledge we just learned. Okay. So what kind of functional group? Okay. One always. Yeah. That's right. Okay. Alcohol. Okay. Perfect. Okay. All right. So if you take a look, okay, so the mass difference between the ion peak and also 82. Okay. So 100 minus 82. Okay. So that should be 18. Okay. 18 means it's the alcohol. Okay. And also if you have one mass spectrum, okay, at hand. Okay. So I will first look at now is any even number of the mass. Okay. So that's not common. Okay. So we actually only learn the two fragmentation case, so can generate kind of even number. One is the alcohol, another is the megalefty kind of the fragmentation case, so 80, 58. Okay, so those please keep in mind. Okay. All right. Okay. So now this is the second kind of the practice. Okay. So we have this fragment case. This is the mass spectrum. Okay. So can anyone tell me what kind of functional group in this molecule? All right, that's pretty good. Okay. Benzene, okay. So someone already taught kind of benzene, okay. So clearly you see kind of 91 peak, okay, 91 peak here, okay. So that's the benzene, okay. So very unique, okay. So normally no other kind of the fragment can give it kind of 91 peak, okay. Right. So that's the mass spectrum can provide some information, but the not as good as the proton NMR and those the carbon NMR and even the not as good as kind of the IR, okay. So but sometimes kind of give kind of important information like chlorine, bromine. Okay. Yeah, here's kind of the real sample. Okay, so the first one is the mass spectrum for cyclohexanol. Second one is the xylene case. So All right. Okay. So now will learn one very important kind of the rule in a mass spectrum kind of the chapter. Okay? Rule 13. Okay, so yeah, take out your calculator. Take out the calculator. Okay, so we'll do some math. Okay, do some math. Okay. So rule 13 is a very important rule. Okay, so yeah, help you kind of yeah, based on your molecular mass. Okay, get here the molecular formula. Okay. And then you get to the molecular formula. Okay. All right. So how do we do that? Okay, so pretty easy. Okay. So I just use the one example can show you the rule 13. Okay. So for example, okay, so yeah, based on the mass spectrum, you already know the molecular mass should be 86. Okay. All right. And the first step, okay, so yeah, you need the divided 86 by 13. Okay. So yeah, just here. So here, okay, so yeah, molecular peak mass. Okay, so ion peak mass. Okay, divided by 13. Okay. 86 divided by 13. Okay. And then you generate some kind of a number. Okay. So I just show the number for you guys. Okay. 6.61538 something. Okay. All right. So once you see this number, okay. So the digital before the point, okay. So this one, okay. So that tell you how many carbon in this molecule. Okay, so that's the 6. Okay, before the point. Okay, that's we see the 6 carbon in this molecule. All right, and then that's the first step. Okay, so yeah, carbon number equals to the digital before the decimal point. Okay, so yeah, so once you divide by 30. Okay. And then second, okay, so the number after point. Okay, so you times 13. Okay, plus the carbon number. That's give you a hydrogen number. Okay, so now we do some math. Okay, this one, okay, point here 6 here 15384. Okay, times 13. Okay, that should give you 8. Okay, so around 8. Okay, so yeah, round up. Okay, and then 14. Okay, so you need to add carbon number. Okay, so we already know the carbon number is 6. Okay, so 8 plus 6. Okay, that's give kind of 14. Okay, so this will be the hydrogen number. Okay, right, and eventually the formula for this molecule is C6H14. Right, okay. So once you done the rule 13, okay, make sure you check DU. Okay, so that's kind of important. Okay, so you have to make sure you degree of saturation kind of make sense. Okay, make sense. Okay, right. So for example, okay, so yeah, I just quickly do it. Okay, DU equals kind of 6 times 2, okay, plus 2 minus 14, and then divided by 2, okay, the whole thing equals 0, okay. DU 0 cancel, that makes sense, okay. So that's here, no problem, okay. All right, okay, so now, you guys take a try, okay. You guys take a try, okay. So, if your molecular mass is, 106, okay. So, take a try, okay. So, what's here the carbon number, hydrogen number for this here, the molecular weight, okay. Mass, okay. Apply rule 13. And after you're done, okay, please also do the DU number calculation, okay. Right, take a try, okay. Not hard, okay. So first, 106 divided by the 13 will generate kind of some number, okay, some kind of small number, okay. And then the number the digital before the point, okay, that will be your carbon number, okay. And then the number after the point, okay, you times 13 plus carbon number, that will be your hydrogen number, okay. Right, take a try, okay. So once you're done, okay, please type your answer in the chat window, okay. How many carbon, how many hydrogen for this molecule? And also type here the DU number in the chat window. All right, okay, so it's pretty good. Okay, so someone already get it done. Okay, right. So same thing. Okay, here 106. Okay, divided by 13. Okay, so here I just write down the answer for you guys. 85. Okay, 15384. All right. Okay. So the point before the digital before the point, okay, that give you a carbon number. Okay. 8 carbon, okay, and then The 14K, so yeah, the number, okay, so yeah, you times yeah, the 14 times 13K. That's yeah, should give you yeah, about yeah, the 2K. Right, so this 2 plus yeah, the carbon number, okay, so that's give you hydrogen number, okay. So that means yeah, this molecule has yeah, 10 hydrogen, okay. Right. And then you go ahead and do the yeah, DO number calculation, okay. DO equals 4, that makes sense, okay, so that's yeah, because yeah, we see some molecule, we see DO equals 4, okay. All right, okay, so yeah, but yeah, for the reality, okay, so yeah, yeah, for one molecule, okay, so yeah, it can have yeah other atom than yeah, hydrogen, carbon, okay, so can have oxygen, carbon, hydrogen, okay, and the nitrogen, sulfur, chlorine, bromine, okay. So in this case, yeah, if you find there's some other atom in the yeah, molecule, okay, you have to do some kind of yeah, replacement, okay. Before that, okay, so little bit keep in mind here, okay, so what's the mass for individual atom, okay? Hydrogen is 1, okay, and then carbon mass is 12, oxygen mass is 16, nitrogen mass is 14, and then sulfur mass is 32, okay? Right, okay, so now we can do the replacement, okay? Right, so if you find there's 1 oxygen in the molecule, okay, so yeah, you just the replace here the 1 hydrogen plus the 4 1 carbon plus 4 hydrogen, okay, which is oxygen. Then that will be kind of the same kind of mass, okay. So yeah, okay. So 1 oxygen mass equals to the 1 carbon, okay, plus the 4 hydrogen, okay, because the 1 oxygen is 16 and then carbon is 12, okay, 12 plus 4, okay, that's also give you 16, okay. Right, and then if there's the sulfur in the molecule, okay, so then you just have to replace the 2 carbon plus 8 hydrogen, okay, because the sulfur mass is the 32, okay, so if you want to keep the mass the same, okay, so you have to replace it by 2 carbon, 8 oxygen, 2 carbon 24 plus 8 hydrogen, okay, so it still give you a 32, okay. And if you find there's nitrogen in the molecule, nitrogen, okay, and then yeah, this time you need to replace 1 carbon plus the 2 hydrogen in the molecule, okay. Okay, and then that still keeps the same mass, okay. So 14 is the nitrogen, 12 is hydrogen, 12 is carbon, 12 plus 2, okay, so still give you 14. And quite often you find there's a helium atom in the molecule, okay, so because we do DO number calculation, you find the DO doesn't make sense, okay. So now we do a practice, okay. Right. So now we try the mass equal to 88, okay. So yeah, you guys take try, okay. So yeah, how many carbon, how many hydrogen, okay, so yeah, can generate from a mass equal to 88, okay, and then yeah, you apply rule of 13, okay. After you're done, okay, so also yeah, please kind of calculate the number for this one. Yeah, take a try, okay. So yeah, apply rule 13 to 88, okay. So yeah, and then what's the formula for this molecule, and then what's the DO number for this one. Yeah, apply rule 13, okay. So 88 divided by 13 will generate some number, okay. So yeah, the digital before the point, okay, that's your carbon number, okay. The digital after the point, okay, you times 13, okay, and plus carbon number, that's your hydrogen number, okay. Try it, okay. So yeah, this is kind of important technique, okay. So yeah, rule 13, yeah, done covering in our lecture, actually kind of our textbook, okay, but yeah, you have to learn it, okay, because that's kind of important technique, okay. So yeah, later we will use it to solve the most difficult question in organic chemistry 1. All right, can anyone tell me how many hydrogen? Okay, so C6, okay, H16, that's right, okay, what's the DO number? Okay, there's no oxygen so far. Okay, right. So we do okay. We still do rule 13. Okay, so 88. Okay, so don't need involve hit your atom very beginning. Okay, so you do it later. Okay, so all right. So apply kind of the rule 13. Okay, so divided by 13. Okay, and then the number should come out of 6.7. 6.923. Okay. All right, so the carbon number should be the C6, okay, and then the following kind of the 933, okay, so times 13, okay, and then plus 6, that's carbon number, okay, so that's give kind of 16, okay, so that means the 16 hydrogen, okay, right. Yeah, that's right, okay, so if you that's so far the formula come up kind of C6H16, okay. So if you do the DO number calculation, DO should be kind of -1, okay. So that doesn't make sense, okay, because the D-ground saturation has to be the positive integral, okay. So whole number, okay. So cannot be negative kind of integral, okay. So that means we have to do some replacement, okay. So if you do some elemental analysis, okay. So sometimes can tell there's oxygen inside, okay. So in this case, we can do is minus the 1 carbon and then 4 hydrogen, okay, plus 1 oxygen, okay. So in this case, okay, the new formula come up kind of C5H12O, okay. Right. Can anyone do the DO number for the C5H12O? Okay, take try. Okay, what's your D ground saturation? Okay, 0. Okay, that's right. Okay, so now it makes sense. Okay, D ground saturation 0. Okay, so okay, that's also showed you here. Okay, so if you find the 1 oxygen in the molecule, okay, so you do the replacement. Okay, so D ground saturation normally increase by 1. Okay, so if there's sulfur, okay, so you do the replacement, D ground saturation will increase by 2. Okay, nitrogen, okay, D ground saturation will increase by a half. Okay, so that's pretty interesting. Okay, all right. Okay. So now we do another practice. Okay, so 73. Okay. So this time, okay, so you guys just take try, okay, so use the knowledge we just learned, okay, so apply rule 13, and also do the kind of replacement, okay, so the heat atom replacement, okay, give me the right formula for this one, okay. So I take try, okay, 73, okay. So what's the right formula for this 73 mass? Yeah, for the all rule 13, okay. So very beginning you don't need to do any replacement, okay. So with the heteroatom, okay? Just general formula with the carbon and the hydrogen, okay. And then following case we have the do DO number calculation, okay. So if you DO number doesn't make sense, okay. So you need to do the replacement, okay. The formula is right, C5H13, but the DO is not wrong, okay. So what's the DO number? Do it again. Yeah, that's right. Okay, 0.5, balance 0.5, but that doesn't make sense. Okay. All right. So now, you need to do some replacement. Okay, generally kind of more makes sense here to the formula. Okay. All right. Okay. Some still got to continue generally kind of here just half for DU number. Okay. That doesn't make sense. Okay. So can anyone generally kind of more reasonable formula? Yeah, that's right. Okay. Finally. Okay. That's right. Okay. Good. Okay. All right. Okay. So for this one, okay, so we apply rule 13 again, okay, so that's should get it kind of 5.61538, okay, all right, so the point digital before the point that should be kind of carbon number 5 carbon, okay, and then this one times kind of 13 plus carbon number, okay, so I just kind of quickly draw it, okay, so should come kind of 13, okay, C5H13, okay. So if you do the DU number for this molecule, okay, so C5H13, okay, that should kind of the minus half, okay. That doesn't make sense, okay. So the DU number cannot be only half, okay. So cannot will also be a negative number, okay. Right, and then you have to do some replacement, okay. So replacement, okay. So you don't randomly try to kind of oxygen, sulfur, nitrogen, okay. So look at here, okay. So this mass is the old number, okay. Old number, we can apply nitrogen rule, okay. Nitrogen kind of normally speaking, now the mass should be kind of even number, okay. But here the old number that means the old number of nitrogen in the molecule, okay. Right. So in this case here the C5 we are the H13, we just here the replace here one carbon, okay. So remember, okay. So one carbon plus two hydrogen equals to the one nitrogen, okay. So one carbon, okay, and two hydrogen, okay, with the one nitrogen, okay. So then C4H11, okay, right, and then you do the calculation, okay. So come to 0, okay. So that's makes sense more, okay. That makes sense more, okay. All right, okay. So here's kind of another example, okay. So this actually you can practice on it, okay. So the 140 case, right? Talking of cyclic ketone, okay. So if you first apply rule 13, come kind of carbon number and hydrogen number, okay, and then because this is ketone, okay, so you have to replace the one carbon, four hydrogen with oxygen, okay, and then you will get kind of right formula, okay. This one you can practice later, okay. All right, okay. So now we do another practice, okay. So this is the mass spectrum, okay, for one compound. It's the molecular ion mass is the 328, okay. Okay, so now you guys try, okay. Try to generate a formula based on 328 mass, okay. So apply rule 13, okay. And after you're done, okay, so please also calculate DU number, okay. All right, try, okay. 328. Okay, so take out the calculator, okay. 328 divided by 13, generate some number, okay. So the digital before the point, okay, that's your carbon number, okay. The digital after point times 13 plus carbon number, okay. So that's your hydrogen number, okay. All right, take try, okay. Again, so once you're done, okay, please put your the formula in the chat window and also the DU number in the chat window, okay. 328. All right, pretty fast. Good. Okay. All right, someone already applied kind of rule 13, come up kind of right formula. Okay, so C25H28. Okay. All right. Okay, and then if you based on this formula, okay, calculate DU number, okay, that should come up kind of 12. Okay. Okay, so that's the 12 kind of huge number, okay, because normally we learn the organic compound, okay, so won't give so high kind of the DU number, okay, so that makes sense, okay. So in this case here, you guys need to learn another important kind of the replacement, okay. So if you come up with a very huge kind of DU number, okay, so if you want to decrease this DU number, what you can do is the minus one carbon, okay, and then replace it with the 12 hydrogen, okay. So for example, for this case, okay, so C25H28 will become kind of C24H40, okay. So you remember, so remember kind of one carbon mass is 12, okay, and then equal to kind of mass of 12 hydrogen, okay. So you do this replacement, okay. So and then you calculate DU number, okay, so I will just gonna quickly show you guys, okay, so DU should be kind of 5, okay, this time, okay. So that makes sense more, okay, that makes sense more, okay, so right, and then this is the right here, the formula, okay, C24H40, okay, so that's come here, okay. So if you come up kind of the DU number doesn't make sense, okay, too high, okay, so then replace one carbon with your 12 hydrogen, okay, so then that's kind of greatly decrease kind of your deal number, okay? Vice versa, okay? So if you come up kind of the deal number, yeah, too low, okay? For example, yeah, -4, -5, okay, something like this, okay? So in this case, yeah, you can replace your 12 hydrogen with 1 carbon, okay? So yeah, just -12 hydrogen, okay? Add 1 carbon in the formula, okay? Then that should greatly kind of rise up kind of the deal number, okay? Increase deal number, okay? So that's kind of important technique, okay? So yeah, we have to learn here, okay? Right, so that's it for today, okay? So yeah, we'll continue. Okay, so yeah, normally speaking, kind of the DU should be less than 8, okay? Less or equal to 8, okay? So 8's kind of 2 bending, okay? So yeah, normally speaking, kind of the 2 bending, that's enough, okay? So yeah. All the okay, right? So we just replace 1 carbon with 12 hydrogen, okay? So replace 1 carbon, okay? 25 carbon become 24, okay? And then you add your 12 hydrogen, 28 plus 12, okay? That's 40, okay? So that's greatly change kind of deal number, okay? So the 24 times kind of 2 plus 2 minus 40, okay? So divide by 2, that deal will be 5, okay? But if you do the deal number for this one, that deal will be 12, okay? So that's how do we do that, okay? All right, okay, so that's it, okay? So have a good day, okay, everyone, okay? So if you have any question, okay, so just come back here at the 8 minutes later, okay? I will reopen the Zoom, okay? Otherwise, have a good day.